he gave us a rather nice look at the Chem operations center downstairs. And when our group was leaving, I asked him a question about something, and I had seen a picture of about a month ago. He said, yes, it was. They're talking about that. It's pretty cool thing.
We'll get to that.
Image not too long ago. So, Maury's been out to tell us about Curiosity, and specifically the Chem instrument.
So, you've already been hearing, and I know some of you know quite a lot about what we've been doing, but it's been certainly the culmination of my career to get to work on this, and it's been very exciting. So I think I told you that the mission was conceived about more than 12 years ago, and then we had there was a request for proposals. The original motivation for this big rover was to be a big step beyond the Mars exploration rovers, and partly because it was developing new technologies for delivering heavy payloads to other planets. So it's partly in engineering. So the heat shield was originally intended to be part of the development for the next generation of NASA human spacecraft and things like that. And this is just like Back to the Future. Our car here is powered by plutonium, so that's pretty cool thing. So this picture was taken about a year and a half ago, and I'll show you the latest version of this of our the latest selfie. We've had many scientists, including a bunch from UNM, and some who are now at other places, and we even have a rock from New Mexico that's been sent to Mars as a standard that was prepared here. Jane and Larry helped Penny King pick out a rock to use as a calibration target for the APXS experiment, and so that's pretty cool. So this sample was polished here in this building, and now it's on Mars on the rover. So the science objectives, the primary science goals are to assess this region for biological potential, geology and geochemistry, the role of water, and surface radiation. So we have a lot of different experiments, and we have synergy with other missions, including great synergy going on, improving now with opportunity at Endeavour Crater. We'll hear from Larry about that tomorrow more. Another aspect is Martian meteorites, and we have a major effort going on here. We're studying this new meteorite called Black Beauty. And Susie Gordon, for example, is using the ChemCam LIBS instrument at Los Alamos, identical instrument to the one on Mars, to analyze the Martian meteorites. And so we can cross-compare the data. So that's a neat thing going on. And then the heritage goes back to the early missions like Viking and life detection results. And one of the early results from Curiosity was discovering the presence of this perchlorate chemical, which helped explain some of the anomalous results or unusual results from the Viking experiments that have been controversial for 25, 30 years. So a lot of neat stuff going on. I showed you, you saw downstairs the public site. There's a ton of stuff on here. And if you go to the raw images, you can look at the very latest pictures that came up. But actually, there's an application for Macs, and only Macs, unfortunately, and iPads, called Midnight Mars. If you want to, or Midnight Planet. If you want to see all the rover, all the Mars images, that's the place to go. It's not a NASA site, but they suck all of the data off of here, and it goes, and it's an amazing thing. I use it for my research, so that's how good it is. Midnight Planet.
Midnight Planet?
Yeah.
Website?
Well, you can download the app. The Midnight app, Midnight Planet app. It's truly amazing what it does. Okay, so here's me. This was with the testbed rover and out of JPL. And before we can do anything with the real rover on Mars, it has to be checked out on the testbed. which is virtually identical to Curiosity. And you get some idea of how big this thing really is. It was really exciting to see this, since I'm a little low on the totem pole and didn't get to go see the real rover before it was launched. So, we actually had a working ChemCam in here. The ChemCam instrument that was up here is now back in France, and we're using that as a laboratory instrument. We also have something called a Scarecrow rover that has the same weight. And so, you know, there's been all this stuff about wheels. Well, the Scarecrow rover has been driven all over the place, all over these rocks. And notice, these are the exact same wheels, and there's no punctures, no holes.
The aliens got it?
Well, we went over an area that had a lot harder rocks than we expected, and a lot harder rocks than were present even in the Mars yard at JPL, and they've taken this rover all over the place to drive it around. Yeah, there's some small dents, but nothing like what we have. This one area that we drove over, which was really nasty. Okay, so the target, Gale Crater on the planet Mars. The thing about the surface of Mars is the same area as the surface of all the continents on Earth. So think about, yeah, it's smaller than the Earth, but where our little rover is exploring a really microscopic portion of the surface of Mars. But in many ways, we now have better imagery of Mars than we do of most areas of the Earth. For the area where I showed you some of you downstairs, you can see the tracks of the rover from our 30 centimeter resolution imagery of the area, and we have basically every wavelength remote sensing data on Gale Crater. It's not quite as complete as I'd like. Now we did have so here's all the landing sites. Phoenix was way up north. Viking 2, sort of similar area. In fact, if they think that ice was we almost scraped down to ice on Viking 2. If they'd gone just a little bit deeper, they would have seen ice. It's too bad they didn't do that. Viking 1 here, Pathfinder, Opportunity and Spirit. The new InSight is going, the next small lander is going to be just north of Curiosity, about in here. And they're having landing site selection meetings for ExoMars from Europe and Russia, and the Mars NASA 2020 rover. And so nothing's been selected there yet. So here we're zooming into Gale Crater, and you can see there's a lot of other big craters that have been filled in as well. It turns out the Gale is actually very deep, one of the deepest craters. And here's a perspective view. And the amazing thing is Mount Sharp here, which is a pile of sediments 5.5 kilometers or 18,000 feet high. And so when you see that picture in the background, that little mound, you're looking at a mountain that's more like Mount Everest than anything else. So very amazing. There is a little bit, I showed you, this is a complex crater. We have terraces. Over here, there's an area that looks like it's part of a central uplift, but most of it has been buried by these sediments. Okay, so this is looking from the side. There's a fan coming down from the crater rim, an alluvial fan, and my house is sitting on one just up here, very similar. Here's a map of it. Here's the crater rim. There's channels coming down and this alluvial fan material. And then there's this distal area down here and we landed about right here, and we just got over into these layered harder rocks. So this was the launch. Who said they got to go see the launch? Oh, you guys, fantastic. So this was really amazing. And so it was a terrific thing to go and see. Here's the descent, heat shield separation. And we're actually using this imager. It was never intended to do work on the surface, but so it's slightly out of focus, but it's looking straight down, and you get to see what we're driving over. And this was the dust being kicked up by the jets, and I was pretty happy about this whole thing. So my wife took that picture. And this was shortly after we landed. The HazCam low down in black and white took this picture, and you could see Mount Sharp there. And so it was very exciting. So this was the first 90 days, 90 sols of Mars time at JPL. And it was pretty amazing what you could see around JPL in the evening or in the early morning before anybody else had shown up. This is in front of one of the main buildings at JPL. So this is our operations going on. This was the door to the one of the elevators. And so here's the mast part of, half of the mast of Curiosity, and this is the daughter of the photographer, so pretty cool. This was one of our early science theme group meetings, so I was telling you about that here and here. At that time, you know, everybody was piling in as we were looking at these new pictures. Nowadays, we're lucky to get, you know, 5 to 10 people to participate. After 2 years of constant activity, it's an effort, but it's a tremendous opportunity for the students to jump in. This was, you know, just on the walls around the building there. And so this is the software that we're using. It's called MSL ICE, and this is the amazing software that we use to run the rover. And I can run that software on my laptop sitting at Starbucks, which is pretty amazing. So it does a range of things. It allows image browsing. We can look at all the images. We can even look in 3D. We can select targets. We can do activity planning and modeling and the sequence development, which the engineers are doing. So this is what it looks like when we're looking at images. And we can say, oh, I want to shoot at that rock. And you click on the rock, and it says create a target here. And then we type in the name of the target, gives you all the distance and elevation and all the information about the target. And then you go on, and and here's another way you can look at the pictures that just came down. It gives you all the information, and then it has the planning. And this is how we plan each day's activities. It's a sequence of actions in this software here. This is the timeline view, and so some instruments can be turned on and left on for a while. This stripe is the beginning of the day when we radio information up to the rover, and then things start happening. And this is a contact science day, so this is where this says we're going to be within this area. We're going to move the arm, and then we're going to turn APXS on and do a measurement, things like that. So this is how the science team and the engineers plan operations every day. So we have a plan for every single day. This happened to be Sol 149. And so there's a plan like this for every single Martian day that's been filled out and then sent up. We've only lost a very few number of sols. Once in a while there'll be a problem. Once or twice the Deep Space Network has had a problem, and we haven't been able to radio the instructions up. So the rover says, oh, didn't receive a plan, and it knows to do a run out and just keep going but not do anything. So various roles. You saw this is our area downstairs. We have different roles for running. So this is, again, some of the early science. This is the landing site area. We blew away a lot of the dust. In fact, the rover, you can see the rover sitting there. And then we realized that this area was very close by, and I had been pushing for some time that this was a part of this alluvial fan and probably had neat sediments that we would be very interested in looking at. And so we decided to drive over here, and we drove down to this area here, explored this, and then took off again. So this is what it looked like landing. Now remember, this is 18,000 feet high. So if you look out at the mountains out there, that's only, so 10,000 feet, so we're at 5,000. So that's 5,000 feet. Imagine 3 times that. So that shows you how big it is. So now we'll talk a little bit about ChemCam, the instrument that we're using. And this is the mast unit built in France, and the body unit built up at Los Alamos. And this unit was then installed inside the cover up here. And then underneath this mast, which again is 3 meters high, we have our wide angle and our telephoto color cameras. And then we have redundant pairs of navigational cameras. And these were actually flight spares from the MER rover mission. They're simple black and white cameras. And I wish they were higher resolution, but that's what we got. So what ChemCam does is it has a laser beam that fires out of the telescope, creates a little plasma, and then the light's collected back by the telescope and goes through a fiber optic cable into the body unit where there's 3 spectrographs. And then, so what really happens, this isn't what really happens, but we get a little tiny, this is looking at the flash, the little plasma flash inside the chamber, one of our Mars chambers. So under Mars pressure, the plasma can expand more rapidly. It turns out that it's just about ideal for us. The plasma gets big enough to send a nice pulse of light back to our telescope, but doesn't just instantly disperse. We can point this thing amazingly well. So we took some from up here. After the hole was drilled, we could look down at the hole and actually fire shots. And then we actually were able to fire lines of shots down the side of the drill hole. And we've done this several times. Now you think about, you take a dime and you stick it across the floor there, and we're able to fire the laser and point it that well. So it's a little trickier than our normal day. We have to take some pictures the day before to make sure our pointing is precise. But so gives you an idea of the size of a dime. This was our very first spectrum, our very first rock called Coronation, and this rock we only hit at one spot, and it gave a nice composition. The first shots, these rocks are covered with dust, as you can see, and there's actually some water absorbed in the dust, and we get a little peak from hydrogen in the first couple of shots. Then we blow away the dust, and we're into the rock. So when we talk about the composition, we always eliminate the first 5 spectra, which are usually the dust. And then this is the first rock we really studied, called Jake Matievich, after an engineer. This engineer had been instrumental with Mars Pathfinder and the MER rovers. He was one of the chief engineers, and he passed away just shortly before landing. And so we named this rock after him. And so we did a lot of different analyses. APXS has a big footprint, and it's a sensor that's about 2 inches in diameter. And then you can see where we fired our laser in a series of different points. This is the APXS spectra. And then we left Glen Elg. So we drove down here and began our work down in this light tone fractured material that we now think was the lake bed of an ancient lake. And so there was the first picture we had showing the rover and the tracks. In fact, the image is almost good enough. I think you can actually see the wheels, individual wheels of MSL, which is kind of amazing. So we drove down, we looked at some neat rocks on the way. Here's some of our first sight of these conglomerates. And I was down at my son's apartment in Los Angeles, and I said, let's look and see what just came down. And it was this picture, and I said, oh my gosh, this is really amazing. This is why we came here. And so, it was pretty cool that to see these pictures before they were released, and literally right after landing, that we really had hit the jackpot on hitting sedimentary rocks.
Excuse me.
Yeah.
The rock you showed us yesterday from Germany.
Right. Yes.
That looks like conglomerate rock as
Yeah.
well. You said the church had been made out of that, and it was actually it was a rock with melt in.
Yes.
How do you know that this is conglomerate and not? What
Excellent question. The impact breccias have angular fragments in them because of the shock and the effects. Whereas this, if you look particularly, like if you look up in here, you'll see that these are rounded. And we have lots of very round pebbles. This isn't the best image to show that, but if you zoom in, you can see really clearly that these are rounded samples. And so this one is really pretty distinctive. Now later on, we've had breccias, and I did show one picture where some of our later conglomerates are not quite as clear. The clasts aren't quite as rounded. But by inference, because we've been driving through this for 2 years, there's pretty good chance that these are also sediments that we're looking at. Not proven. So anyway, this was one of our first times when we shot at 5 different spots. We shoot typically about 30 laser pulses at each spot, and then look at the data. And we can plot up the chemistry, and that's what Susie's doing, looking at the chemistry of the rocks. And our beam is pretty small, about 0.5 millimeter. So we hit individual grains, like feldspar grains. So here's an example. We hit little feldspar grains, and then we hit some high iron titanium points, and the dust fell here. This is titanium versus iron. So we can learn a lot of information about the rocks. So this was our original landing site ellipse. We actually landed down right there, and then studies before landing showed that we had this alluvial fan coming down here, but we're down at the distal end here. And so it was a little more, people were wondering what we would find. Well, as we approached, we also, the first thing we did was we stopped at this place called Rock Nest, this drift, and did some sampling. We used our scoop and dug out, and you could see the wall of the ripple, but there's also all these small rounded particles, which is interesting. Here's the scoop full of the material. So we can drill, or we can actually scoop stuff up and then put it in and do the analysis here. This is gases released. So in the SAM experiment, which has 3 instruments, it has a quadrupole mass spectrometer, a tunable laser spectrometer, and a gas chromatograph mass spectrometer, all in a box this big. And my colleagues said they'd die to have one of these in their laboratories. It's super sophisticated. And then we also have X-ray diffraction, and we have an X-ray diffraction lab downstairs, and we got the first pattern, and so that was pretty neat. And then nearby, we also got, we discovered that there's, in the second drilling, we discovered that there's a lot of clay in the rocks down there, and we'll get back to that. So then, so we drove down here to into Yellowknife Bay. We passed this area called Shaler, where we saw these cross-bedded rocks, and the experts on our team are certain that these were laid down by water, not sand dunes. And this is the view off across. It's just totally unbelievable. I mean, this is the most scenic place. It's just amazing. Off in the distance is the crater rim. And these are, we thought, in fact, my colleague, Wolf Elston, who's in his 80s, helped map this. He was actually at JPL when Mariner 4 flew by Mars, and he helped us do some mapping before we landed of this area. And he said this really looks like the mudstones in some of the valleys and dry lakes in the Southwest. And sure enough, that's what we think it is. So very neat stuff. So this is the area we investigated in great deal. We spent months in this area here, including doing drilling. And there's interesting stuff. This is a ChemCam RMI image from our telescope. And you can see that there's veins. Well, this is the Earth. There's a pocket knife. And we see things just like that on Mars with these sulfates, calcium sulfates. And we analyze those. There's nodules, spherules, suggest water is, this was not only laid down in water, but water has sat there and percolated for a long time. Now here's an example of where you can see these rounded pebbles. And this is a really nice collection of gravel. You would, put that in your garden very nicely. So, but there's weird cracks that suggest that there's void spaces underground, and the dust is going down into these. We then did some drilling. We have these veins, these ridges we've investigated. Here's the site where we drilled, and this is the sampling system and drill system. This whole unit is about that big around, about like a lawnmower. And on one side it has the drill. The other side over here it has the alpha proton X-ray spectrometer. Over here it has a MOLLE camera. Here's the brush. And Chimera is the sample handling sieving apparatus and scoop. And so then we can brush this off. We can use we can measure the chemistry with the APXS. And then here's a picture of the brush. And so we've done all this. Here's a picture of the arm. We don't have a lot of pictures of the arm because we use the camera that's on the end of the arm to take a picture of the rover. Then we Photoshop out the little bits of the arm. That's how those selfies were made. So, but this is a neat picture. You can see Mount Sharp in the background. You can see the erosion, the way the erosion is working here by eroding back these scarps. The rates, which is something I've been working on, are, so you can tell, okay, it looks kind of like you'd see out in the desert here, right? There's this nice scarp, so you know this is kind of eroding back here. The winds blow and erode this away. But the vertical rates are about I'm calculating about 8 to 15 millimeters per million years. And I just read this morning about a paper that just came out about the Himalayas. The average rates there range up to 700 meters per million years. About 1 million times slower on Mars. So things do not happen fast. So we think these rocks were laid down about 3 billion years ago. And so here's a picture of the drill bit. This is actually I think they said they bought it at the hardware store. So it's a percussive drill, hammer drill. And then here's the scoop. So after they drilled it, the sample goes up through the system, gets sieved, and can be dumped into the scoop. So you can use the scoop to examine what you drilled, or you can actually use the scoop to scoop stuff up. So this was actually the powder that we scooped up that came from the drill. And then that's this is the other drill. So here are laser shots into the tailings from the drill. And in fact, Ryan Jackson's working on a small paper about the analyses of these and the drill hole walls. And here you can see more marks from the laser. So this is how we study things. And then one of the neat things from this was the in this mudstone, we have these low angle reflections in the X-ray that suggest that you had clays present. And that's a sign that there was water, a lot of water around. This was probably a lake bed. which is really a lot what we were hoping to find. Unfortunately, the sample that went into SAM didn't see any complex hydrocarbons that you might expect. In other words, no signs of life, even though there were a lot of interesting details. In fact, here's one small part of the kinds of stuff that SAM gives us. This is as it heats up a sample, things come off like oxygen, carbon dioxide, sulfur, water, and our biogeochemists worry about that stuff. So we think we found this habitable environment at Yellowknife Bay because we have clays and we have all the ingredients. So that's pretty neat. We also were even able to get an exposure age from the isotope analysis with the mass spectrometer of 78 million years. This is part of the information that I've been using to worry about the erosion rates. Okay, then we left and more recently have driven down from here down to through Dingo Gap to the Kimberley. We stopped at a couple of spots, and then here's where we were pretty recently, where we did some more drilling. And so this was our first big dune that we went over, blocking our pathway through Dingo Gap. And there's some very interesting things here. Notice that there's these rocks that are rolling down from here. And there's rocks coming down from here. But where are the rocks here? There are no big rocks left. And our experts on aeolian processes suggest that what is happening is you have sand blowing along the floor of this, and that's what's eroding away the rocks. In fact, you can see this rock down here looks eroded. And these are called venifacts. It's the technical term for a rock that's been eroded by wind. So we're looking at, on the Earth, you'd see something like this, and it might have formed, you go up to the lava flows or something, and it might have formed in the last, couple of thousand years or 100, 50,000 years. This has probably looked like this for 100 million years. Only slightly different. So pretty amazing. So here's the rover tracks coming down here. We do the donuts when we turn. We spent some time here analyzing this area. Then we came down to this area. Here's Curiosity sitting there. And then we moved down to about here where we did the drilling. And so here was the view. This is view from this location, right about here. I think, yeah. And you can see these spectacular layered sedimentary rocks. Really very cool. And so we've been doing, the chemical analysis with ChemCam. We have analyses of all these rocks. Now we're, starting to talk among the team about who's going to write up different papers about the results. So this is where we stopped to do the drilling. This was just about 2 months ago. And there was this interesting slump that occurred of the piled up dust. And then this is the rock surface. We did all kinds of analyses. Here, there's a very interesting sample. When we stop, we have a chance to do a lot more ChemCam than usual. And this little sort of grayish patches of rock here we hit and turn out to have very high manganese. And we do have high manganese deposits in the desert called desert varnish. But this doesn't look like it's that. It looks more like a vein, some kind of vein deposit. And my former student, Nina Lanza, who's now a postdoc up at Los Alamos, is writing some papers about this. And it will be very, very interesting. And, if you're worrying about life and microbial life, veins that have been deposited by water is the sort of thing that is very interesting. So worry about that. So here's a picture of the latest drill hole called Windjana, the Windjana drill hole. And again, we fired the laser beam and made these nice series of points. Here's another set of ChemCam spots up here. So each one of these spots, we get about 30 sets of spectra. So that's a lot of data that we have for each of this. So it takes a while. So this is the most recent selfie by MSL. And this is right at the Windjana area. In fact, you can just make out the drill site right there. And of course, you remember where ChemCam is. It's pretty easy because the next thing you saw was the laser beam firing out of there. Actually, I drew that in this morning, but the laser beam is incredibly small. In fact, Nina has fired the laser at her wedding ring and made a bunch of little teeny tiny pits you can barely see on her wedding ring just to be able to show it off. So that's kind of cool. But this shows you what we're doing now, and in a way it shows how we're doing more complex stuff than we did before. This was one of the most recent things in June. We spotted this iron meteorite, and unfortunately, because for various reasons we drove on by and didn't even do an analysis, which I think was a mistake, but there's very big competing interests on what we do. And so we don't get to always go and see the interesting things. But it's pretty definitively an iron meteorite. It's quite a large one too. So there's a good chance that this fell millions of years ago, and it's just been is part of a lag on top of the surface. This is probably not where it originally fell. Probably the dirt's been eroded out from underneath it, and it's just slowly been sitting there. You can see in this image that our telescope, our ChemCam, gets really nice images, and much better than the central portion here. This area here is a big mosaic of the images taken with the telescope from our ChemCam instrument.